All right, so our goal today is to do some kinematics. I hope that you remember kinematics from first semester. It was our entry unit. It's where we did this kind of, I don't want to use the word garbage because I am recording this. I just find it to be the most boring stuff that we do. Remember, we started with graphs of like velocity and time, and from here we talked about a graph like this. The slope of this line would be the acceleration, and the area under this line would be the displacement. That all ring a bell to you guys? From there, we developed a series of relationships that we called Galileo's motion equations. And they had things like v equals at plus v naught, and delta x equals 1/2 at squared plus v naught times t. And I could keep going. I'll do one more. 2a delta x equals, not x, v squared plus v naught squared. Sorry to bore you. JK. LOL. I didn't say anything was wrong with them. They're just not for me. They're super sweet, and I probably could. I just don't buy them. So I'm sorry. I'm glad I'm recording this though. So when somebody talks about, well, Mr. Shelton, he just hates Pop-Tarts. I'm like, it's not that I hate them. It's just, I mean, you have choices of foods out there, right? When I go to choose foods, I don't have to choose Pop-Tarts. There are other alternatives. So this is measured in meters. These two are measured generally in meters per second. This is meters per second squared in seconds. We know these were vectors. Right. And we had names for them all: displacement, initial velocity, final velocity, acceleration, and time. These are the translational variables. Translational motion. These objects are changing position. As you can imagine from our conversation so far, for an object that is spinning, there are going to be a complementary set of variables for rotational motion. And they are going to look very similar. But instead of delta x, when an object is changing the direction it's facing, it moves through an angle. So we say delta theta. We already had an introduction to the symbol we use for angular speed. It was omega. So we will have omega naught and omega final. They'll represent the angular velocity or rotational velocity. We're going to use a lowercase alpha for acceleration. We're basically just taking the same letter that we use for our English letters and using the Greek equivalent. Last is T for time. So these are also vectors. We talked about the right-hand rule. We talked about accelerations and torques and velocities when it came to the door. So we understand that these have direction as well. But more importantly, they come with their own set of units. Now, I'm just going to slide this over a little bit more because these represent the rotational kinematics variables. One of the big differences is first semester we tended to not play around with the units very much. Our things were given in meters per second, and you didn't have to do much to deal with that. But second semester, that's less true. Revolutions, rotations, radians, degrees, it's all fair game. You're supposed to be fairly good at being able to go between all of these. For velocities, RPM, rotations per minute, RPS, rotations per second, radians per second. We'll never use degrees per second, that won't come up, but these will all be used, and your ability to move between them will be tested too. And of course, for acceleration, we're talking about radians per second squared. We don't really use anything else besides that, so if you're asked for acceleration, you're very likely going to have to convert all of your numbers into radians, and time stays the same. So, translating the motion equations into our rotational variables should be something I don't have to do with you. I would expect that if it's V equals AT plus V naught, you could recognize that there's kind of a one-to-one correlation between these things. So any place you see a V, you'd put an omega. And every place you see an alpha or an A, you'd put an alpha. And every place you see a V naught, you'd put an omega naught. So I don't want to do this for all of them, but I will say that several of these are already in your equation sheet. You should note where they are so you can find them. But the big three, I say that because these are the ones that are on the equation sheet. You should probably work at committing to memory, but there's a total of 5. We can use all the different ones that we have. They all work the same way because we're really talking about the same thing. However, my experience has been that students struggle with these kinds of problems, either because they've forgotten everything from first semester or bad words. So let's practice, because I don't want to get stuck with all that baggage. I think you guys could do one of these. In fact, I'm sure of it. But I also want to point out that I'm going to clearly try to see if you are capable people, meaning you remember what we talked about last semester. Let's say this is a record player, and a record player spins a long play record at 33 1/3 RPM. Let's say from the moment you switch it on to the moment it's ready to play the record takes 10 seconds. What angular acceleration did the record experience? And how many revolutions did it spin through? All right? And I'm definitely calling on David. He's got his calculator out, and he's going to do it all in his head because he has no paper. So I'm prepared. You've got let's go with 30 seconds. I want this in radians per second squared, and this in rotations or revolutions. Now, I'm under the distinct impression you remember first semester how to do some conversions here. We'll see if you can parlay that into actual work here now to help remember. All right, so I'm going to be kind. I don't know why, but I'll try. Probably because I was so mean to somebody earlier by saying that they were a negative person. Oh, it's you. So, 33 1/3 rotations per minute. I start with unit multipliers. I find that they leave the least possibility for making mistakes, but they take the longest to do. So I don't mean this in a cruel way. I think you look like I think you look less capable as a person when it comes to your mathematics if you screw up simple conversions. So instead of having to remember whether you divide or multiply by whatever, unit multipliers will ensure you get it right every time. And I'm going to show you a trick about it too in a minute. Let's go ahead and convert rotations per minute to radians per second. You can only do one conversion at a time. So if I wanted to convert 33 1/3 rotations per minute to radians per second, let's start by getting rid of pick one, rotations or minutes? Rotations, so I take rotations, which is in the top, I write rotations in the bottom, so I have to write it on the opposite side of the line. And then and again, I'm not saying all of this because I need to know it. I'm giving you a set of instructions that you could write them down. So when I say it's in your notes, it actually is. And not just a string of these parentheses, which means nothing because you've never done it or you can't remember how to do it. So whatever's in the top, write the same thing in the bottom and write what you're going to in the blank. So I want to go to radians. Now you know your conversion facts. If you don't, you can look them up. Some of them are even on your equation sheet. But for every one rotation, there are 2 pi radians. Go to my next conversion fact. Minutes, I write them on the opposite side of the line they're currently on. I write what I'm going to on the other line. And then write in my conversion fact. Then multiply across on the top, multiply across on the bottom. The minutes cancel, rotations cancel. I'll be left with radians per second. It's like we're multiplying by a 1. This is a 1. That's why it doesn't change the value. It changes the units the value is expressed in. Now, the reason why I like unit multipliers is for this singular purpose. What if I tell you that you have an acceleration that is 35 let's go with rotations per minute squared. Most of you can convert something like this because it doesn't have a square in it. But once there's a square in it, that changes what you have to do. So for those of you who don't know how to do this conversion, this is why I like unit multipliers. Let's convert this to radians per second squared. It's not part of the problem, but let's do it so you know how to use unit multipliers in a more effective way. We'll handle the easy one first. We know how to deal with rotations. Done. But I need to deal with minutes. So I put minutes here. I put seconds here. I still use my same conversion fact. 1 minute, 60 seconds. But this unit is squared, so you square the multiplier. And that does the conversion. So again, I like unit multipliers. They allow for more flexibility, and they work better when you have a complex unit. Like what if it's kilograms meters per second squared, and you're having to convert that into something else? That's why unit multipliers are way more effective. And they also allow you to go from bigger changes. What if you have to go from minutes to days? You probably don't know that one, but you probably know the chain of conversions that would get you there. So that's why I stick with unit multipliers. That should be enough to get you started to finish this problem. This comes out to be, I think, 3.45, if done correctly. And you need that because that's going to be your final velocity. And your initial velocity is 0. You're looking for the acceleration. The time is 10 seconds. And you also want the displacement. So that should give you a pretty... Delta theta.
I just call it the double because I forgot what it actually is.
That's okay. Omega minus omega naught?
Yeah.
Or plus omega naught?
Yeah.
Times t?
Yeah.
Okay. That works great. Something to keep in mind, this answer, if you use the numbers that we have here, will give you an answer that is in radians, but you're asked for the number of rotations. So you had to convert your answer to rotations. Or, and I want to throw this at you since you're taking notes right now and there's a few minutes left of class, I know that the final velocity was 33 1/3 rotations per minute. That's already in rotations. 10 seconds is 1/6 of a minute. You don't have to always convert to radians. If your problem is already in rotations in minutes, you can just put everything in minutes, and then you'll get an answer that is in rotations. But of course, you could have done 1/2 times 3.45 plus 0 times 10. This will give you an answer too, but this answer is in radians, and this answer is in rotations. You will have to convert this to rotations. Multiple choice questions, right? This is where you're going to see this kind of stuff. You know that the thing that they're going to have as choices are going to be you not converting correctly, which is going to have the effect generally of you seeing an answer that you get out of your calculator, but you didn't convert, and therefore that answer's wrong. This is a good example too. They're going to have both answers there. They're going to have one, and they're all going to have the same unit. But one is you effectively not converting correctly or forgetting to convert at all. Try again. Something else? You're riding a merry-go-round. You notice that it makes one rotation every 3 seconds. When the ride is over, it takes 2 rotations to come to rest. So, obviously, we don't have enough time, but finish this tonight. Or start doing your homework because you have enough information to do your homework now. But I want to know what was the acceleration in radians per second and how long did it take? Goodbye, class.